Welcome to the second part of Chapter 5 of Basic Steps in Magnetic Resonance. One of the most important manifestations of longitudinal relaxation is the nuclear Overhauser effect. Now, nuclear Overhauser effects were postulated by a theoretician, Albert Overhauser, in 1953. So initially, Overhauser postulated that the effect that now carries his name would occur in solids, and more specifically in conducting solids, such as lithium metal. He said that if we have lithium metal, there are conduction electrons, and some of them have unpaired spins, and therefore there is an EPR resonance, and we can saturate that EPR resonance by microwave irradiation. And Overhauser then predicted that if you heat up the electrons in this fashion, you would cool down the nuclei so that the amplitude of the NMR transitions of lithium-6 or lithium-7 would actually be enhanced by the irradiation. This is a paradox, and many physicists of those days did not believe Overhauser until Charlie Slichter came along and actually proved experimentally that Overhauser was right. And then it was discovered that this was not specific to conducting metals, but also possible in liquids, and it is in fact Lionel Solomon at the École Polytechnique in Paris who proved this to be correct and also developed the appropriate theory. Now, in this chapter we shall not be concerned with the case of metallic conductors such as lithium, but focus on isolated pairs of nuclei in a molecule which is in a liquid, and the molecule is tumbling with a typical correlation function. So if we have two spins immersed in a magnetic field, as we know, we have a state where the two spins are parallel with the magnetic field, we have a state where the two spins are anti-parallel, and we have a case where one spin is up and the other is down, and of course the reverse is also possible. So between these four states we know that we have observable transitions. In fact, we have two transitions that belong to the X multiplet, and we have two transitions that belong to the A multiplet. That we discussed in the chapter dedicated to scalar couplings. But we also have longitudinal relaxation processes, and those go with rates which are called W, and W in fact is probability in German. It comes from the word Wahrscheinlichkeit, and in fact I believe that it is Wolfgang Pauli who used this W first to explain relaxation in multispin systems using the so-called master equation. Now, this in fact is just a transition probability, and it turns out that you can distinguish the transition probability where a single spin, namely spin A, is flipping. So from here to here, only the first spin flips from beta to alpha, whereas the second spin doesn't move. So this we call the single quantum probability that A is flipping. Likewise, this transition is in most cases has the same probability, whereas these two transitions are distinct in that it is now spin X that flips, but again with a single quantum flip, and therefore we call this W1 of X. More surprisingly, there is also a probability, very important, of a so-called flip-flop process, also known as a zero quantum process, because there is no overall absorption of any quanta. One quantum is emitted and one absorbed, and therefore we have zero quantum. In this case, both spins A and X participate, so this is known as a W0AX. And finally, there is also the possibility that spins that are in the beta-beta situation fall down all the way to the ground state in the alpha-alpha position, and this is known as a double quantum process involving both spins A and X. So the energy levels for a homonuclear pair of spin 1/2 nuclei A and X actually hide a tremendous wealth of information. If we wanted to see what happens with the flow of the populations, we have the so-called master equation, where we can write the populations of these states, for example, n beta beta, n beta alpha, n alpha beta, and n alpha alpha. We can make a vector of those, and we can say that there must be some time dependence, and then we can make a matrix here and look at the deviations of these different populations from their thermal equilibrium. So if these deviations vanish, then we are in a stationary state and nothing happens. But if somehow the deviations are non-vanishing, then we shall have the non-vanishing time derivative of the populations driven by the deviations from the thermal equilibrium. So all of these have delta NAJ is equal to NAJ minus NAJ equilibrium. And this matrix W is a 4x4 matrix, and you can easily fill in the different elements here. You should also know that the diagonal elements are equal to minus the sum over the off-diagonal elements on the same row, I different from J. That means that there is a conservation of populations, and then if a population is taken out of one of the levels and put into another level, overall it is conserved. So with reference to the matrix W of transition probabilities, there are really only two that matter to explain the Overhauser effect. There is the double quantum probability, where both spins A and X flip at the same time, and it turns out that this is proportional to the spectral density taken at twice the Larmor frequency. So recall that the Larmor frequency omega 0 would be 2 pi times, say, 400 megahertz. Then twice that is 2 pi times 800 megahertz, etc. The Overhauser effect is also crucially affected by the flip-flop probability, that is to say, the zero quantum probability, and this turns out to be proportional to the spectral density at the origin, or if you prefer, to the probability that the molecule does not undergo any rotational motion at all. So if we plot the spectral density on a linear scale, so not a logarithmic scale now, then we see different behaviors. A small molecule, such as, for example, H2O, could rotate at very high speeds without falling apart. And in fact, it turns out that the probability of rotational diffusion is about equal at all sorts of frequencies in the scale, and we speak of a white spectrum. In analogy to the light that comes to us from the sun, where all colors are equally represented, so that their superposition gives the feeling that the light is white. Well, of course, these are not visible colors, these are radio frequencies, but all colors are equally represented, and the spectrum is again white. If, on the other hand, we look at a large object, such as a protein, for example, then it is obvious that it cannot undergo rotational diffusion at very high frequencies, because it would fall apart, it would sort of disintegrate because of centrifugal forces. And consequently, high frequencies are essentially forbidden, and the protein is compelled to be content with slow motions, and consequently the likelihood that it does not move at all, which is represented by the spectral density at the origin, is much higher than it was for the simple case of water. Now we see that if we look at the spectral density at the Larmor frequency, for the protein it is not completely negligible, but it's much higher for water. And if we look at twice the Larmor frequency, then it goes essentially to zero for a large protein, whereas for water it's still about the same, regardless of frequency. The dependence of the probability W2, the double quantum probability, and of the zero quantum probability W0 on the correlation time is as follows. For the zero quantum, the flip-flop rate, it is simply proportional to J of 0, and it turns out that this simply increases. The bigger the molecule, the slower the tumbling, the higher that rate. For W2, the situation is a bit more complicated, because when we go from very fast tumbling to slower tumbling, W2 first increases and then reaches a maximum, which is in the vicinity of omega 0 equal to 1 over tau c, and then it drops again towards slower tumbling or higher mass. So clearly there is a crossover point where these two things cancel each other. It turns out that there are some analogies between Overhauser effects as we observe them today in proteins and, generally speaking, in liquids and solutions, and the Overhauser effect that was originally predicted to occur in conducting solids such as lithium metal. And what we see here is the energy level diagram of a two-spin system in a liquid. And it turns out that if the scalar coupling is 0, then the two lines of the x nucleus, the two parallel transitions here, are degenerate, and in fact we only see one single peak at the chemical shift of spin X, and likewise the two transitions of spin A are degenerate, and we see only one line at the chemical shift of spin A. Now we can instruct our radio frequency source and our NMR spectrometer to selectively irradiate the resonances of spin X, the two superimposed resonances. It turns out that if we do that, we shall equalize the populations across the X transitions and in fact demagnetize those transitions, and as a result the signal will vanish in all of these cases. But if we look at what happens with the A transitions, in some cases it is amplified, as we see here. So in other words, the peak gets more intense, whereas in another case it's actually reversed. This depends on the conditions. And clearly something very peculiar has happened, because you might expect that irradiation of spin X will warm up the spin system and therefore also saturate spin A, but that is not the case, and that is precisely the paradox that Albert Overhauser discovered. So the nuclear Overhauser effect actually results from an interplay between relaxation and irradiation. And relaxation tends to drive us back to the Boltzmann equilibrium. Before we address the Boltzmann equilibrium, we should look at the ways of distributing the population among the four states. So if we look at our two coupled spins again, then we should focus attention on the deviations of the populations with respect to the demagnetized state. If we have a demagnetized state, then all populations, alpha alpha and alpha beta and beta alpha and beta beta, they would all have 0.25. That's a demagnetized state. And what we see here is these two white balls tell us that the beta beta state is depleted with respect to the demagnetized state, whereas the alpha alpha state is populated more than in the demagnetized condition. And if we do some accountancy, we see that between the alpha alpha state, which has two black symbols, and the alpha beta state, which has no symbol at all, there is an advantage of 2 minus 0, which is 2 delta. The same is true here, and it turns out the same is true here. You have 0 minus minus 2, which is also plus 2. Now, the next thing that we have to do is that we have to saturate the X transitions. So here again we have the thermal equilibrium with a depleted beta-beta state and the populated alpha-alpha state. And if we now started irradiating the X transitions, that means that we deliberately equalize the populations here. So basically what we do is we promote one of these black balls to the upper level, and likewise we also saturate these two transitions, which means that we basically bring down one of these white balls from the top to the beta-alpha level. So at this point here, once the saturation has been achieved, which can be done in a few milliseconds or so, then we have a new distribution, but we still have a simple difference of 2 delta between this level and this level. That's plus 1 minus minus 1, or here again plus 1 minus minus 1. These transitions of spin A have not been changed. Okay, so we have discussed that we can go from the thermal equilibrium situation here to this partly saturated state where the X transitions have been saturated, that is to say their population differences have been annihilated by irradiation, whereas these have been preserved. Now the Overhauser effect comes about because we have flip-flop or flip-flip transitions. The probability here, W0, that's the zero quantum flip-flop transition, will tend to go from right to left in that the excess population that we have in the alpha-beta state will tend to fill up the deficiency of the population on the beta-alpha state. At the same time, of course, this horizontal process has no effect whatsoever on the populations of the top state and the bottom state, and consequently these are preserved, whereas the central states are depleted. One of the consequences of this is that the difference in populations between +1 minus 0 is now just 1 delta, whereas it was 2 delta here, whereas in this case the population difference is 0 minus 1, which is also +1 delta, so instead of 2 delta. In other words, we see an attenuation of the difference in populations across these transitions compared to what they were before the W0 process set in. A more puzzling aspect occurs when the double quantum probability W2AX is dominant. We shall see that this is only possible for small molecules, so this is the pathway for small molecules, whereas this pathway was predominant for large molecules, such as proteins, for example. As we know, small molecules have a large flip-flip probability W2, and that means that there will be a tendency for the populations to go from the top level to the bottom level. Now you might say there is already a difference in populations, so why should we go to a larger difference? Well, the reason is that in thermal equilibrium there was indeed a larger difference. We had difference of +2 minus 2, which is 4, from 4 delta between these two extreme transitions. And since relaxation tries to return to thermal equilibrium, the result of W2 relaxation is to increase the deficit here from 1 white ball to 2 white balls, and to increase the population from 1 black ball to 2 black balls. Now this is quite remarkable, because now we see that the difference in population across the A transition here is +2 minus 1, which is 3 delta, and likewise here it is 1 minus 2, which is 3 delta again. So now we have, with respect to the 2 delta difference here, we have an amplification here, amplification of the difference in populations, and also of the signal that we shall observe, whereas here we have a simple attenuation. So the nuclear Overhauser effect is often described by this parameter eta here, which is defined as the intensity of the signal that we observe in the presence of RF irradiation minus the intensity that we observe in a normal spectrum, normalized by the intensity that we observe in the normal spectrum. And it turns out that if we have an amplification, then eta will be 0.5. This is typically the case for a homonuclear system in a small molecule. But if there is an attenuation, then we can go all the way to -1, and that is the case for slow tumbling and large molecules. We're talking here about a steady-state Overhauser effect, which is somewhat distinct from the transient Overhauser effect that we shall exploit in macromolecules. Now it turns out that such things also exist in heteronuclear systems, and in that case eta is 1/2 of the ratio of the gyromagnetic ratio of the spin x that we irradiate divided by the gyromagnetic ratio of the spin that we observe. It turns out that there are Overhauser effects in heteronuclear systems, in which case this parameter eta is equal to 1/2 of the ratio of the gamma, the gyromagnetic ratio of spin x that we irradiate, saturate, divided by the gamma, the gyromagnetic ratio of the spin that we observe. So if we consider carbon-13 as an observable nucleus, then the eta that we obtain when we irradiate the protons would be equal to 1/2 of the gamma of the protons divided by the gamma of the carbon-13, and this is about 1/2 of roughly 4, and this is about 2. And consequently, when you look at the equation, we have a threefold enhancement, because the amplitude goes from 1 to 3. But be careful, if we look at other nuclei, for example nitrogen-15, which is very popular in biomolecules, then the eta that we obtain when irradiating the protons is equal to the same ratio, and it turns out that this is 10 over -1, because the gyromagnetic ratio of nitrogen-15 is negative, so this turns out to be about -5. So this means that if we have a nitrogen-15 spectrum with a small positive peak, if we do not irradiate the protons, we may observe a large negative peak if we do irradiate the protons, which is rather surprising. In fact, this is one thing I didn't believe myself until I did the experiment many years ago. We should remember, by the way, that the Overhauser effect is not always 100% efficient, and sometimes we get less than the predicted maximum, and sometimes we get exactly zero if we stuck halfway between positive and negative. In this case, I forgot to say that the carbon-13 spectrum goes from this to about this, which is an enhancement of a factor 3. That is very commonly observed and indeed very welcome. This concludes part 2 of this chapter. Thank you for your attention.